Look at the surface of the sun. It is a violent environment, constantly throwing off deadly solar radiation that drifts right into Earth's path. The only reason our atmosphere isn't stripped away is a protective, invisible magnetic shield. That shield is actively generated by something called the geodynamo. 3,000 kilometers beneath our feet, there is an ocean of superheated liquid iron making up Earth's outer core. As that molten metal swirls, it generates electric currents and, consequently, our magnetic field. For decades, historical observations led researchers to a clear consensus about how this deep Earth engine operates. The assumption was that the outer core flowed in a relatively stable pattern, moving predominantly from east to west. The habitability of the planet's surface relies entirely on the predictable churning of this deep Earth machine. A steady flow meant a steady shield. In 2010, the rules governing that planetary engine abruptly broke, and satellite data pinpointed the exact location, deep beneath the Pacific Ocean. This map of the core shows normal, stable westward directional arrows. But right here, under the equatorial Pacific zone, a broad region of the iron-rich liquid suddenly stopped moving west and strongly reversed its flow to the east. An unexplained reversal of this scale means the outer core isn't the stable environment researchers thought it was. It raises an immediate question about what is actually happening to the engine that keeps our planet safe. To monitor a deep Earth anomaly from the vacuum of space, scientists rely on missions like the European Space Agency's SWARM and CryoSat. These highly sensitive satellites fly in precisely coordinated orbits. This allows them to filter out the magnetic noise generated by the Earth's crust and oceans, giving researchers a pristine look at the deep geodynamo. This timeline plots magnetic field changes from 1997 to 2025. Notice the sharp spikes marking the 2010 eastward reversal and the 2017 geomagnetic jerk. Recently, the data twists again. Since 2020, that intense eastward flow has actually begun to weaken. A sudden reversal, followed by a weakening a decade later, shows that the outer core is a highly dynamic system, capable of rapid, massive shifts in just a few years. To figure out why the liquid core reversed its flow in the first place, a team led by Frederick Dahl Madsen at the University of Edinburgh had to look deeper. They found that the sudden flow shift in the liquid outer core perfectly coincides with changes happening further down, inside the solid inner core. The team hypothesizes that the liquid outer core's strange behavior doesn't happen in a vacuum. Instead, it is directly driven by deeply hidden shifts occurring in the solid metal sphere at the absolute center of the planet. The Pacific anomaly shows that Earth's deepest anatomical layers do not operate independently. They act as a highly interconnected, responsive planetary system. The decades-old textbook model of a steadily westward flowing core is now officially obsolete. Moving forward, researchers are looking at three possibilities. This eastward surge might be a temporary fluctuation, a brand new baseline for core circulation, or a tiny part of a long-term oscillation cycle we haven't monitored long enough to recognize. These deep Earth dynamics happen far below the surface, and they pose no direct danger to human life or the climate. However, they absolutely dictate the future shape and strength of our magnetic field. Because that magnetic shield is constantly shifting, the systems that rely on it have to adjust. This shifting shield directly impacts the accuracy of global GPS and everyday navigation systems that keep modern infrastructure running. A changing magnetic shield also alters our models for near-Earth space weather, which directly affects how we operate spacecraft. To ensure the safety of our near-Earth space and technology, we now have to maintain a continuous, unblinking watch on the complex ocean of liquid iron 3,000 kilometers below us. Red dwarf stars make up about 3/4 of all the stars in our galaxy, making them the most obvious places to look for new planets. One of these stars sits right in our cosmic backyard. At just 28 light-years away, Ross 318 is a relatively close neighbor. But stars like this are incredibly volatile. Their surfaces churn constantly with intense magnetic sunspots and violently erupt with massive solar flares. For astronomers trying to observe them, this constant magnetic activity generates a hurricane of visual and gravitational noise. This split-screen visualization shows exactly how a dark sunspot rotating across the star's surface generates identical light-dip line graphs to an actual planet. The sunspot mimics the shadow and gravitational pull of a real world, creating a frustrating false positive known as an alias. Because stellar aliases look practically identical to actual planets in the data, confirming a genuine alien world around Ross 318 required astronomers to somehow isolate a whisper inside a hurricane. A team of astronomers from Italy and Brazil realized that short-term observation wouldn't be enough to cut through that interference, so they compiled a massive 15-year baseline of historical and fresh data. To filter the noise, they started with radial velocity data pulled from two highly sensitive spectrographs, Carmenes and HIRES. This diagram illustrates radial velocity, tracking the physical wobble of a star pulled by an unseen planet's gravity. They then layered space-based photometry from TESS, watching for rhythmic dips in starlight caused by a planet crossing in front of the star. Sunspots eventually decay, meaning the noise they generate behaves erratically over long periods of time. But the physical footprint of a real planet remains mathematically rigid across both the wobble and the light dip datasets. By comparing decades of overlapping data, the team systematically deleted the erratic stellar aliases, isolating only the permanent, repeating anomalies. Once the static was successfully stripped away from 15 years of observations, a clear, undeniable planetary signal pierced through. The data revealed an exoplanet, now designated Ross 318b, completing an orbit around its host star exactly every 39.63 days. This diagram visualizes the gravitational data, which tells us this is a heavy world. Its minimum mass weighs in at least 6 times more than Earth. In terms of sheer size, its predicted radius is approximately 1.74 times larger than our home planet, and it sits close to its star, separated by only 0.16 astronomical units, which is well within the orbit of Mercury in our own solar system. Pulling these specific physical measurements out of over a decade of chaotic stellar noise proved the team's layered filtering technique was a complete success. That incredibly tight 0.16 AU orbit presents a climatological paradox. Because it sits so close to the star, Ross 318b is likely tidally locked. Tidal locking means the planet's rotation has synced with its orbit. One hemisphere permanently bakes in starlight, while the opposite side freezes in pitch-black night. But the planet's extreme weight creates a counter-effect. A mass of 6 Earths strongly suggests it possesses a thick, substantial atmosphere. An atmosphere of that size acts like a planetary conveyor belt, taking the intense heat from the dayside and blowing it over to warm the freezing night side. This global redistribution of heat gives Ross 318b an estimated equilibrium temperature of roughly 237 Kelvin, or negative 33 degrees Fahrenheit. This places the planet securely within the conservative habitable zone. Because it is temperate, likely has an atmosphere, and is located just 28 light-years away, this super-Earth is a premier candidate for atmospheric characterization, a process of scanning the chemical makeup of its air called transmission spectroscopy. Astronomers already have the ultimate tool waiting to perform that analysis, the James Webb Space Telescope. Finding a temperate super-Earth so close to home is a massive discovery, but the data layering technique used to uncover it proves that we now have the mathematical tools to strip away magnetic stellar static, clearing a path to discover countless other worlds currently hiding in the noise. Have you ever reached the bottom of a soap dispenser, added a little water to get that last bit out, and pressed the pump, only to get a splash of barely sudsy water? The thin water jets right through the thick gel instead of pushing it out. Physicists call this mechanical failure viscous fingering. It is a fluid dynamics instability that occurs whenever a runny, low-viscosity liquid is forced into a much thicker liquid inside a confined space. The thinner liquid simply hunts for the path of least resistance. Instead of forming a solid wall of pressure to push the thick fluid forward, the runny liquid shatters that barrier. It pierces the boundary layer, creating a series of advancing, tree-like channels. In a soap bottle, this is a minor annoyance, but at an industrial scale, this microscopic branching behavior results in a significant loss of mechanical efficiency. For example, to extract heavy crude oil from the ground, energy companies often pump highly pressurized carbon dioxide into underground reservoirs. The objective is to use the gas to sweep the heavy oil toward the extraction wells. This process is also central to carbon sequestration, where engineers attempt to inject gigatons of captured CO2 deep into subterranean saltwater aquifers for permanent storage. But viscous fingering sabotages both of these operations. The injected gas shoots straight through the thick oil or the dense saltwater. It bypasses the target fluid entirely, often escaping back to the surface while leaving the carbon we intended to trap behind. Large-scale carbon storage and industrial fluid extraction are both limited by this microscopic boundary failure. The stability of a fluid boundary is dictated by three variables: how easily fluids mix, the difference in their viscosities, and injection speed. Fingers are triggered when the initial interface between the runny and thick fluid is flat, sharp, and abrupt. In a laboratory, stopping the fingering is simple. You can slow the injection speed down to a crawl so the runny fluid has time to seep in, or change the chemical makeup of the fluids until their viscosities are nearly identical. But in the field, this creates a paradox. High-volume operations cannot afford to pump fluids at a glacial pace, and engineers cannot change the natural thickness of the oil or salt water found miles underground. We have been attempting to stop a physical instability using variables that the requirements of industry and the reality of geology refuse to let us change. This is why a physics team at the University of Chicago, led by Sidney Nagel, looked for a different solution. They wanted to know if they could stop the fingering without altering viscosity or speed, simply by changing the shape of the interface itself. The team used a testing apparatus consisting of two flat parallel plates separated by an extremely thin gap, filled with a high-viscosity liquid. In their baseline test, they injected a thin liquid through the top plate. The advancing edge formed a blunt, flat face, and viscous fingers formed almost immediately. Then they introduced a process called shearing. While injecting the thin fluid, they began rapidly sliding the bottom plate side to side. This lateral motion forced the boundary into a new geometry, morphing the flat edge into a smooth, pointy curve. With this pointy shape, fingers took much longer to form and grew at a fraction of their normal speed. The experiment demonstrated that fluid stability is directly correlated to the structural geometry of the interface. This provides engineers a way to bypass the constraints of unchangeable viscosity ratios. While this was discovered in a laboratory, it suggests that future underground injection wells could be engineered to induce physical shearing as fluids are pumped into the earth. By controlling the geometry of the leading edge, we can reliably lock carbon dioxide into saltwater aquifers, ensuring the gas stays trapped deep underground. Efficiently managing these industrial flows depends on mastering the microscopic shape of the interface. This image shows a typical spiral galaxy spinning in space. The bright, star-forming regions catch our eye immediately, but the math behind its movement tells us that an enormous, invisible mass is actually dictating how the whole thing rotates. We call it dark matter, and it accounts for the vast majority of the mass in the universe. Despite being everywhere, dark matter behaves completely like a ghost. It almost never emits, absorbs, or reflects light, and it passes right through regular matter without leaving a trace. Physicists do have a leading suspect for what this ghost actually is. It's a hypothetical ultralight particle called the axion. To catch it, researchers have spent decades engineering massive, highly sensitive experimental detectors, pouring enormous financial and theoretical resources into the hunt. Every single one of these machines is built on a specific baseline assumption. They treat axions as a classical field, searching for smooth, continuous ripples that act a lot like standard electromagnetic waves. That means billions of dollars and generations of scientific effort hinge entirely on the premise that axion dark matter behaves exactly like a classical wave. But we live in a strictly quantum universe. At the microscopic level, smooth classical physics breaks down into discrete, jittery quantum states. Axions, as physical particles, have to follow these rules. Recently, rapid advancements in quantum technology have given researchers the tools to look closer at these subatomic behaviors, leading to an uncomfortable realization about our current methods. If axions are inherently quantum particles, and our detectors are specifically tuned to look for classical waves, are we using the wrong instruments altogether? The fear was very real. There was a strong mathematical possibility that current searches were entirely blind to the target, meaning we had been hunting dark matter the wrong way all along. This is the University of Chicago, where a team of researchers recently joined forces with colleagues at UC Berkeley and Lawrence Berkeley National Lab to resolve the crisis. They threw out the old assumptions and built a completely new end-to-end mathematical framework rooted strictly in the laws of quantum mechanics. The goal was to simulate what a modern instrument would actually record if it actively tried to detect the axions' hidden, erratic quantum properties. They laid this new quantum representation side by side with the older classical models to pinpoint exactly where the data would diverge. This was the ultimate stress test for the physics community. It would prove if decades of classical experiments were scientifically sound or entirely obsolete. The results revealed a strange paradox. Axions possess distinct quantum effects, but detectors will never perceive them. First, axions have weak interaction strength. Their individual quantum signatures barely register. Second, due to sheer abundance, instruments are hit by an overwhelming flood of axions. The chaotic volume hitting simultaneously forces the quantum variations to mathematically cancel out. The law of large numbers forces the axion's innate quantum noise to suppress itself. What's left behind is the perfect illusion of a smooth, continuous classical wave. You might wonder what would happen if we just built a better machine, an optimally designed futuristic detector specifically calibrated to hunt for those exact quantum blips. The math shows us the absolute physical limit. To gather enough data to see through that massive washout effect, a flawless, perfectly calibrated experiment would have to run continuously for longer than the entire age of the universe. Hitting that temporal brick wall proves something profound. Directly observing the intrinsic quantum effects of axion dark matter is an absolute practical impossibility. In almost any other area of science, discovering that the specific trait you're studying is completely undetectable would be a career-ending disaster. But for dark matter researchers, this impossibility is actually a massive theoretical triumph. Because the quantum effects permanently hide themselves behind their own sheer volume, the classical wave illusion they create is completely flawless. It confirms that the decades of legacy models framing axions as classical fields are absolutely valid. The physics community hasn't been doing it wrong after all. The immediate practical impact is immense. Physicists can confidently push forward with current detector designs, knowing they aren't missing any hidden quantum signals. And as a bonus, these exact same mathematical rules successfully validate the detection methods we use to hunt for gravitational waves. By proving that the axion's quantum nature is permanently out of reach, scientists secured the exact mathematical evidence they needed to keep the hunt alive. The next generation of electronic sensors and photodetectors are currently being assembled at the microscopic level, layer by ultra-thin layer. The foundation of these new microdevices relies on a class of two-dimensional nanomaterials called exenes. But working with these materials comes with a massive physical challenge. They are exceptionally fragile, averaging a thickness of just 5.4 nanometers. For context, a single strand of human DNA is roughly half that wide. To turn those raw, delicate films into functioning chips, manufacturers have to subject them to harsh chemical washes, lithography, and photoresist development. Here is the problem. If you want to check whether that 5-nanometer film actually survived the chemical bath, the traditional method requires physical probes or cutting cross-sections. Testing the material destroys it. Without a reliable way to measure these materials midway through the assembly process, manufacturers are essentially building the future of electronics completely blind. A joint research team from Germany and Israel devised a workaround that requires zero physical contact. This diagram illustrates a technique called imaging ellipsometry. Instead of using a physical probe, the team bounces a continuous beam of polarized light directly off the MXene-coated wafer. When that light hits the sample, the physical properties of the nanomaterial twist and alter the polarization state of the light as it reflects back toward the sensor. The system translates that specific distortion into precise physical data, mapping out the exact depth and composition of the thin film layers. Because the light interacts with the material's electronic environment, the sensor also picks up on charge transport properties. This allows researchers to calculate exactly how well electricity moves across the film without ever making an electrical connection. By turning a simple beam of light into a multimetric sensor, researchers can quantify the health of the material without a single physical tool ever touching it. Zooming out from the microscopic view, a single microchip device on a manufacturing line spans several millimeters across. This creates a logistical headache for quality control. Manufacturers need to rapidly scan the vast macro area of the chip, but they also need to verify structural details down to a single micron. This graphic represents the team's two-pronged approach. To handle the speed issue, they use spectroscopic microellipsometry. This acts like a high-speed sniper rifle, firing off a rapid, targeted single-spot check on a specific point. To map the broader structure, they switch to imaging spectroscopic ellipsometry. This is the floodlight approach, sweeping across the entire thin film device. A single scan connects the millimeter-wide macro view directly to incredibly dense micrometer details, maintaining high resolution across the whole surface. Balancing fast single-point spot checks with comprehensive spatial mapping provides a complete picture of the device's structural integrity. Placing these optical tools directly into the fabrication timeline solves the initial problem of those harsh manufacturing steps. Researchers can now track spatial variations and watch the material properties evolve in real time, right as the lithography and photoresist chemicals wash over the chip. Because they can see these local changes mid-process, engineers can directly correlate specific structural shifts during manufacturing to how the final device will actually perform. This method isn't limited to exonenes. Because the sensor is designed to detect subtle polarization changes on any surface, it can analyze a wide range of 2D and anisotropic materials, essentially anything where the molecular orientation affects the light's behavior. This non-destructive feedback loop allows labs to optimize their recipes and verify thin film uniformity, providing the data needed to move these fragile components from experimental prototypes towards reliable fabrication. To build the next generation of computing, engineers are attempting something incredibly difficult: combining electronic signals, electrical arcs, and coherent light beams onto a single, hyper-fast microchip. But capturing and directing light at that scale requires specific physical architecture. A photonic chip needs nanoscale optical gratings, precisely spaced grooves designed to catch a single beam of light and split it into a specific spectrum. If you've ever tilted a compact disc back and forth to see the rainbow reflections along its surface, you've seen a macroscopic version of this exact mechanism at work. Currently, carving these microscopic structures into silicon requires extreme heat, multi-million-dollar cleanroom facilities, and extensive chemical baths that leave behind lingering residue. Material scientists have long proposed a theoretical shortcut. Instead of carving the patterns step by step, you could simply apply mechanical stress to wrinkle the surface into a perfect shape, all in a single motion. The problem is the material itself. The insulators we rely on for microchips, like silica and silicon nitride, are deeply rigid and brittle. If you apply lateral compressive pressure to a flat sheet of glass, it doesn't fold, it simply shatters. For decades, the accepted rule in material science was that mechanical wrinkling techniques were exclusively limited to soft, elastic substrates like polymers. Manufacturers are left with a severe physical contradiction. To achieve hyper-fast, light-integrated computing without the massive overhead of traditional fabrication, they need a way to fold rigid glass as if it were paper without causing a single crack. Researchers at Rice University recently bypassed this rigidity limit by building a highly specialized two-layer material stack. The bottom layer is a simple, standard piece of rigid silica, the exact same insulator currently inside everyday microchips. Sitting directly on top of that silica is a semiconducting crystal called alpha molybdenum trioxide. This specific crystal possesses a physical property known as anisotropy. Its internal atomic lattice behaves entirely differently depending on where the pressure comes from. Squeeze it along one axis and it compresses randomly. Squeeze it along another and it folds into perfect directional rows. When placed under mechanical stress, this anisotropy crystal survives the pressure. Instead of turning to dust, it gracefully buckles into highly organized nanoscale ripples. This top crystal layer functions as an entirely mechanical stress engine laid directly over the glass, primed for activation. To activate this two-layer sandwich, the team places it under an electron beam at room temperature. As the beam strikes the material, it triggers two simultaneous physical reactions. First, it irradiates the bottom layer, causing the atomic bonds within the hard silica to rapidly vibrate and loosen. Even without any applied heat, this atomic rearrangement causes the brittle silica to soften and slowly deform, taking on the physical traits of a yielding plastic. At the exact same time, the electron beam applies intense directional stress to the top anisotropic air. The crystal reacts to this specific pressure by buckling into uniform, repeating waves, creating perfectly spaced ripples far smaller than the width of a human hair. Because the silica directly beneath it is now soft, the buckling top crystal violently stamps its organized wrinkles downward, leaving a perfectly matched impression in the yielding glass. The electron beam effectively exploits the physical properties of both materials at once. It uses the internal geometry of a crystal to physically bully a rigid insulator into a completely new shape. The moment the electron beam is turned off, the reaction stops. The silica's atomic bonds stabilize, instantly locking the glass back into its deeply rigid state. With the stamping process now complete, the top alpha molybdenum trioxide layer is simply peeled away from the rigid silica. What remains is a clean, fully rigid piece of glass featuring perfectly organized, light-guiding nanoscale wrinkles permanently molded into its surface. There is no chemical etching involved, there are no secondary processing steps, no extreme temperatures, and zero manufacturing residue left behind. This chart illustrates how manufacturers can tune the final design. There is a direct upward correlation between the thickness of the initial anisotropic crystal layer on the x-axis and the resulting nanometer width of the optical ripples on the y-axis. Engineers can adjust this pattern even further by dialing the intensity of the electron beam up or down to modify the specific depth of the wave. The research team has already successfully applied this exact method to other critical insulators widely used across semiconductor manufacturing, including aluminum oxide. By solving the physical paradox of wrinkling glass, material scientists have bypassed a massive manufacturing bottleneck, providing a room temperature shortcut that clears a highly practical path for the next generation of hyper-fast, light-integrated microchips.